I started off with the original design. While already an ergonomic and well-balanced design, a rounded peg is used instead of an angular ledge to connect the sleeve and the casing. For my different approach, I put the casing on top of the cup to measure the temperature of the steam arising from the liquid. However, I realized that measuring the steam would not be as accurate as measuring the coffee outright. One issue with both of these designs was that the sensor was relatively high up on the cup. Hence, once the user consumed enough coffee for its surface to dip below the sensor, we can no longer accurately gauge temperature. As a result, I decided to put the sensor at the bottom of the cup to detect temperature no matter how much coffee is left. To keep the sensor in place at the bottom, I designed the sensor casing with four prongs that perfectly fit the crossing platforms at the bottom of the sleeve, which trap the sensor between the crossing platforms and the coffee cup when the prototype is assembled. Effectively, the prototype doubles as a coaster, avoiding table scalding in addition to being a sleeve, all while mimicking the form factor of the cup itself. Other design decisions include using 5 mm thick walls and removing excess material to reduce cost and printing time. Additionally, an open concept design allowed for more air and measurement. For instance, if the casing was too wide for the sleeve, it may simply stick out through the openings. In Inventor, I inferred the example design that I needed 4 centimeters of space to house the ESP32 and sensor. I also noticed a 1 centimeter deep hollow area under the Tim Hortons cup that I used. Thus, I extruded the sleeve design to be 4 centimeters tall and designed its top with a circumference of about 21 centimeters, which was the circumference of the cup 1 centimeter from the bottom. As a result, my design leaves about 4 centimeters of space between the hollow bottom of the cup and the thin bottom of the casing, which would house the upward facing sensor. In roughly an hour, I 3D printed the parts using Prusa Slicer. I also developed the code in Arduino IDE for the ESP32 microcontroller. After initializing the I/O pins, resistance is sampled from the circuit, which is used to calculate temperature via the Steinhart-Hart equation. Via serial communication, temperature was displayed in the Arduino shell every 500 milliseconds. Initially, I only soldered the thermistor and the resistor and used jumper cables. However, there wasn't very much space between the cup and the sleeve, so I cut, stripped, and soldered 1 centimeter wires of the circuit while inserting them into the ESP32 female ports. So this is the finished prototype with some steaming hot water. Due to the sensor's calibration error, the apparatus actually reached 35 degrees at room temperature. Notice that the cup fits snugly into the sleeve as I lift them both off at the table. The steaming water is pretty hot, so also notice that the temperature will eventually reach roughly 49 degrees before I remove the cup, and finally as the sensor cools off, we revert back to around 35 degrees room temperature. In retrospect, I forgot to burr a hole in my casing for the USB entry. I also did not take dimensions of the physical Arduino chip, so it was a bit loose in the casing. I also didn't extrude the sleeve high enough, meaning that it didn't climb high enough up the cup and often slipped off. And also just where it was, with such a low amount of extrusion, it was difficult to hold. So in future iterations, I would hope to address these issues.